Thank you for joining me to discuss the ins and outs of each of the science and engineering practices. My name is Eddie Walsh, and I want to start us off by having us consider a phenomenon you could explore if you and your students were examining events in space.
This is the first direct image ever taken of a black hole, courtesy of the Event Horizon Telescope. Creating this image required more data than any other scientific experiment in history. So how did they do it? Up until now, most measurements of black holes were indirect, like this time-lapse of stars at the center of our galaxy. The stars seem to be orbiting around something with a humongous gravitational pull. Scientists predicted that thing was a black hole. Astronomers have also seen massive jets of matter emanating from the centers of galaxies, sometimes much larger than the galaxies themselves. They predict that the only thing powerful enough to create them would be black holes. The gravitational waves detected by LIGO in 2015 were the most direct and compelling evidence for black holes to date. But detecting gravitational waves is sort of like hearing a black hole. Scientists still wanted to see it. But how do you take a picture of a black object against a black background? The answer: backlight it. Matter should emit radiation as it heats up while circling the edge of a black hole, the event horizon. With a big enough telescope, scientists should be able to use that radiation as a backdrop to see the silhouette of the black hole itself. But it's tricky. Even though the black hole is gigantic and has galactic scale impacts, it is so far away. To get an image of high enough resolution, scientists calculated they'd need a telescope the size of the Earth, which is obviously impossible. Enter the Event Horizon Telescope, which is not in fact one telescope, but a network of 8 observatories spread around the world from Hawaii to Antarctica. Each observatory provides a tiny piece of the puzzle. Take repeated readings as the Earth spins, and you can capture more angles from each telescope. Once you have enough pieces of the puzzle, algorithms can fill in the gaps and build up the whole picture. This process is called interferometry. The observations used to create this image were made over a few nights in 2017. Each night, each observatory gathered the same amount of data as the Large Hadron Collider does in a year, and it has taken 2 years to piece it all together. With this image, we can see a black hole for the first time, but it's much more than images. It provides precise tests of predictions of general relativity. And what's more, beyond the event horizon is a place where physics as we know it no longer works. This is the first direct image ever taken of a black hole, but coded in its pixels. Could be the answers to questions about the whole universe.
A quick and easy way to get students thinking about what they just saw would be to have them document what they notice and what they wonder about the video they just watched. After some quiet time to work independently, students can share out their notices and wonders in their pairings or groups before collaborating and selecting their top notices and wonders. As we lean into the science and engineering practice of using mathematical and computational thinking, it would be a good opportunity to ask students to consider what they noticed and wondered about the phenomenon that might have included the use of math or computational thinking to observe black holes. If a student or group of students already began evaluating the math behind space observation, be sure you use that student-generated observation to lead into this next part. After having students consider the phenomenon generally, you can then have students reflect and consider what they notice and wonder about the video they just watched, paying special attention to the incorporation of math and computation to support their findings. When participating in science lessons, students generally do not have the opportunity to use math and computational tools to validate the alignment of their findings. In many cases, sums and averages are the extent of mathematical thinking students experience to support their conclusions. This lack of heavy lifting can make it difficult for students to consider phenomena scientifically, since math is so frequently used as a common measure between investigations. Only with frequent planning, implementation, and reflection on the implementation of mathematic and computational tools can students gain a finite sense regarding the scientific information they use to build their own scientific understandings. I want to go ahead and fully introduce myself. My name is Eddie Walsh, and I am the Region 6 Instructional Science Coach working with the Idaho Department of Education. I am based out of Idaho Falls, but myself and the other Idaho science coaches are happy to meet you wherever you are in your science education journey. Our sole focus is to help teachers plan, teach, and assess around the Idaho Content Standards for Science. I wanted to take this opportunity to focus on how we can approach the science and engineering practice of using mathematical and computational thinking. If you have further questions about how the Idaho Science Coaches can help you with your teaching goals, feel free to reach me at my email or visit our Idaho Science Coach website via the QR code or Idaho Department of Education website. When the National Academies of Science, Engineering, and Medicine developed the three dimensions of the framework for K-12 science education in 2011, the science and engineering practices were recognized as perhaps the largest shift educators would need to address to engage students in the immersive experience that is science. Asking students to use mathematics and computational thinking means giving students the opportunity to structure investigations along lines of scale, proportion, and quantity so students can develop a comparative sense between phenomena. I would make it my recommendation right now. If you want your students to progress in processing scientific information independently, do it as often as you can. While students may initially find integrating mathematics and computational thinking to be confusing and time-consuming, with frequency and practice, students will be able to complete math more efficiently and with a more mature sense for the continuum scientists observe by using math in science. Science from the past includes math you can present to students to get them to think about the validation and handling of science data. Most famously, Albert Einstein was able to take his theory of special relativity and simplify it into a succinct equation that just about every student can recite: E equals mc squared. Students can quickly understand the relationship between the variables of energy, matter, and the speed of light. By changing one of the quantities, students can figure the resulting change in the relationship between variables. Katherine Johnson was a feature at NASA for her computational mind and was calculating the trajectory of space missions before computers came to become the integral tools they are today. Katie Bauman took the massive data sets collected through the physical telescopes scattered around the globe to create a computer-based telescope that stitched together the first image ever collected of a black hole. While these examples extract physical science concepts, math can be found in all disciplines of science. By incorporating mathematics into their methods, each of these scientists were able to better convey their thinking as static and proven mathematical or computational statements. Integrating the science and engineering practice of using math and computational thinking needs to look differently at each step in the K-12 student experience. We, as teachers and administrators, recognize when one grade band or another doesn't provide students opportunities to advance in their math skills, we limit student potential throughout their entire learning progression. Imagine students only understanding phenomena in terms of big or small, light or heavy. For science literacy, students need to have a quantitative understanding of the principles underlying phenomena. The K-12 skills progression document on the Idaho Department of Education website breaks down the experiences students should be able to navigate to stay on track with peers locally and nationally. This document provides teachers with starting points for imagining a range of student experiences that allow students to build competency in the range of skills associated with using mathematics and computational thinking. When laid out in this way, we can provide clearer feedback to students and scaffold more for students who find implementing math and computing to be a difficult, or challenge students who have shown early mastery in the SEP. It becomes important to remember students often do not master a standard in a single instance, so planning several opportunities for students to flex all of their science-based math skills within a grade band is critical for all students to stay on track in their science progression. If you are exploring any science standards around the observation of space, you may explore the work of Dr. Catherine Devine at the College of Idaho. Dr. Devine used data gathered at the Very Large Array Radio Telescope in New Mexico to document the properties of star formation through observation of an infrared dark cloud. Even after measuring the emission of ammonia and dicarbon sulfide towards the infrared dark cloud, math and algorithms were essential tools to map the placement and behaviors of materials observed in space. Tracing the same configuration of the Very Large Array Radio Telescope Dr. Devine includes in her research, scientists will come to the same conclusions through her application of mathematics and computational thinking. Again, this is an incredibly heavy application of math in science contexts, but it should inform the progression we hope students can access as they acquire essential science and engineering practices. If you are looking for strategies to bring mathematics and computational thinking to the forefront of your teaching, I have a few materials you may consider if you feel this will be a rough start. PhET simulations operate under computational parameters, and the data integrated in the simulations can be useful at extracting math-based methodologies. Code.org offers students a variety of lessons to familiarize students with the roots of computing. Sometimes lessons like those found in PhET or Code.org help students understand the consistency underlying scientific laws and theory. Vision Learning offers resources to support some of the fundamental mathematics applied in science settings. The Applied Math and Science Education repository is admittedly very difficult to navigate, but there are quite a few useful case studies, simulations, and problem sets to support math and science. The MathWorks Math Modeling Challenge offers resources as well as competitive opportunities for students to apply math in their science learning. While the opportunity is presented in some progression resources for math and computational thinking, it would never be expected for students to master R software for data analysis in high school. At the same time, advanced students would be well suited to learn how to use the technology and implement it in their research. In addition to all of these resources, I would definitely recommend you find an opportunity to collaborate with a cool math teacher in your school who appreciates math and science. Thank you for your time as we've covered how math and computational thinking can help students access authentic science learning opportunities. Hopefully the understandings and strategies outlined in this video make it less stressful to bring instruction around math and science to your students. Please do not hesitate to reach out to me or anyone on the Idaho Science Coach team to clarify anything about the standards.